So good afternoon, everybody. Thanks a lot for coming this afternoon here. For me, it's a big pleasure today to have here Michael Debije. He is an associate professor in the research group called Stimuli-responsive functional materials and devices in the Eindhoven University of Technology. Before that, he did a PhD in the United States. Then he moved as a postdoc in 2000 in the Netherlands. And then from 2003, he joined to the group of stimuli-responsive functional materials and devices. He works with many in different topics related to the control of light in built environments. Quite well recognized for luminescent solar concentrators, but is working also with infrared control windows for the printing polymers in as actuators, and also as a luminescent solar concentrator photo microreactors. I think he, of some of these topics, is going to provide us some information today. And he works in different applications. He does quite a lot of applied research, works in greenhouses, energy saving, energy productions in building environments, but he works with architects, farmers, with different types of peoples and of different profiles. And he has also spin out different companies. Some of them apparently, we discussed this morning, were quite successful. So there is hope for those of us that are working on this. And before giving to him the word, I would like to read a quote that I found in his webpage, which I quite liked. And it says, "I revel in bridging the traditional gaps between disciplines and between academics and society." So I think we can recognize some of us in working in a similar philosophy. So with this I finish. I leave the words to Michael, and thank you for coming.
Thank you very much for that very kind introduction. I'm very happy to be here to give a talk of the Nanoseminars in chemistry. It's also great to see such a full room. I see I brought some of the weather of the Netherlands with me. I was kind of coming here looking forward to getting a suntan, but okay, I guess I have to wait till next time. But let's see here. Yeah, I'm going to talk today on the luminescent solar concentrator, and I titled it Shining Light, New Light on an Old Idea. So, and I hope this is going to go. So I have to hit this one here somewhere, and haha. Luckily, we have technical experts. Okay. So first, a little bit about who SFD is, the Stimuli-responsive functional materials and devices. We're 4 faculty, 4 researchers, a postdoc, and 16 PhD students at last count. So we're not super big, but we develop polymers with new functionalities and try to integrate them into devices to meet industrial and societal challenges. So we're located in the south part of the Netherlands. The major areas we work in are sustainable energy, water management, and healthcare and personal comfort. I'm responsible for the sustainable energy branch, but these are little videos of different types of topics that I work on. But I'm going to be primarily discussing meeting an energy challenge today. And that is the fact that buildings are using 40% of our energy. I think many of you have heard this number. But when you consider the costs for heating, cooling, and lighting, the energy use of these aspects of a building, all of these are related to how poorly we manage sunlight. For example, many times during a cloudy day, well, on a sunny day, they close the curtains, and then when the sun comes out, they forget to reopen the curtains, and we have the lights on. That's bad use of sunlight. Or we have to spend much of our time cooling things or heating things because we don't control the sun. So why has this not been widely addressed? Well, one of the problems is you have to cover such large areas to make it work. And if you cover a large area, they can't be expensive. They have to work when it's shaded or when it's sunny. They have to be able to take a beating. So if it's at ground level, they're going to come into contact with a kid kicking a soccer ball against it. It has to survive. But very importantly, and often overlooked, they have to look good. So the traditional solution is a photovoltaic. And photovoltaic panels you can find everywhere, but not always the most integrated into the built environment. So these are photographs I found on the internet of what I consider some rather poorly chosen ways to integrate solar energy, either because you have to cover just one side of a building, or you have some beautiful orange roofs that you have to offset with these black tiles, or this beautiful curved surface on a building that you lose that curvature because you have to put flat panels on it, and so forth. So what I am trying to, let's say, bring into vogue is the luminescent solar concentrator. So the luminescent solar concentrator was first thought about in the late 70s in trying to find a solution for the high oil prices. And essentially, they're a simple object. You may or may not know them. I've got only two hands, we'll see. So that's just a simple luminescent solar concentrator. It's just a simple piece of plastic. You fill it with a fluorescent dye that absorbs light that is incident on the surface, that emits the light, and a lot of it is trapped inside the panel by total internal reflection. Then at the end, you could put a solar cell. So a very simple concept. Some of the advantages are you can have, pretty much any color and shape. So this is just an example of something that we made. These have back-mounted solar cells, but you put them on the side to hide the cells. They're pretty robust, so I can take this plate, doesn't damage it. So if you do that with the silicon solar cell, you can guess what happens to it. So they're tough, which is something then you can put into a built environment. They're relatively low cost. I mean, the most expensive part of this is not the dye, it's not the solar cell, it's the plastic. So the raw material plastic is the most expensive part. It works very well in scattered light. So you can see there's almost no light or very little light in this room, but you still have some glowing edges. I'm collecting light from anywhere that hits it, then I can concentrate it to an edge. They can be transparent. So this is an example. We made a noise barrier with these. So this is the world's largest luminescent solar concentrators, about 5 to 6 meters long and 1 meter high for the red and the orange plates. And as you can see, it allows a driver to have a rather pleasant thing to look at. Plus you can see through it. So it's transparent, or at least translucent. And it generates a little bit of power, as well as doing the primary function, which is blocking sound. So it's a noise barrier with a payback time. They can also be flexible. So this one's made of a PDMS, polydimethylsiloxane. So you can also have something that would be flexible. So, well, you can say, Mike, this is a great idea. So why aren't they already everywhere? Well, they only have modest efficiencies. So it's not something that we're not trying to compete with silicon. Because for your rooftop, by the way, how many of you have solar cells on the roofs at home? Nobody? 1, 2. Okay, we have 2. So the question is, why not? Why don't you have panels on the roof at home? How about somewhere in front? Why aren't there panels at the roof at home?
Living in an apartment.
Okay, yeah, an apartment. So it's not really appropriate like putting it on a wall, right? You can only think about putting it on a roof. Anybody because it doesn't look good, or I think that's something that comes around. So, but also the efficiencies are low. Why are they low? Well, I've listed here 9 losses that are inherent in the system, all the way from light passing through because it's not absorbed, light being emitted off of the surface, light being reabsorbed by other molecules, and so forth. So my goal is try to improve the performance to get to a modest efficiencies and give you about 30 to 70 watts per square meter. So if you compare that to your panels at home, which are probably rated 180 to 200 watts, this seems quite low. However, this I can go for kilometers along a noise barrier. That's much harder to do with silicon. So the idea is large area, low output, but in total, you can get a lot of electricity out. So I want to try to attack several of these losses. I'm going to talk about first absorption by the light guide. So this is the first thing I did when I started this research way back in the middle of the 2000s. And this is something that's often overlooked, is just the light guide matrix. So if you take a piece of plastic, if you just look at it, all plastics look pretty much the same. Yeah, they look kind of transparent. I've got an example of 4 here, and I've got a pointer on it somewhere. Let's try this one. Nope. Then let's try this one. Okay. So I've got 4 different plastics listed here. Also quartz and glass are in there. But the key ones I want to look at are the orange and the violet. So these are polycarbonate. That's a very common transparent polymer. They sometimes use it for automobile windshields, for example. It's a very tough material. In fact, this is polycarbonate. there are two different quality or two brands of it. You'll see there's an absorption profile, and you see this really little dip here at around 680 nanometers. So normally when somebody looks at this plate, they say, those are pretty much the same, right? This is just a small little absorption peak here. It's not a big deal. But if you're talking about a luminescent concentrator, light is not traveling through the thickness. Light is traveling along a length. So the more absorbance you have here, the more losses you're going to get. And the actual output effect of only a 5 by 5 centimeter sample is the difference from this orange to this violet. So it's really important to choose the right light guide. So that's something, one of the first things that got me going on luminescent concentrators is that even these simple things people hadn't looked at. So I said, okay, what other simple things could we do we might be missing? One of them is they're just single color. Can we make something that's maybe more attractive? So what we did is started to inkjet print images in a fluorescent ink on a blank light guide. So here's some of the examples that were generated from the imagination of one of our students. And you can see you can make beautiful images, really personalized. And all of these, you stick a solar cell on the side here, we can generate electricity for it. And quit jumping. So you don't have to have simply large energy plants to generate megawatts or black roof panels. You can make things localized and personal. So imagine a bus stop with, and this is a skyline image of Eindhoven. Put solar cells on the edge of this, and you have a bus stop that can generate enough power to maybe run the schedule sign, for example. In this way, you don't need to connect up to the grid. So you can have a standalone bus stop. And since it's plastic, it's very difficult to knock that thing down. In Eindhoven anyway, every time PSV wins a championship or loses a championship, everyone in the town is smashed, right? Well, this one, hey, you can't smash this polycarbonate. So we have actually a spin-off company. These images, this is an actual luminescent solar concentrator. This one's different. It has LEDs on the edge. So in the daytime, you collect energy and charge up a battery. At nighttime, you send that light back in and light the LEDs to light the sign. So standalone lit signage with any sort of image. So if you're interested, check out Lusoko, who's trying to commercialize this. Okay, so other things we can attack. Light emitted outside the capture cone, that's the number 2, and reabsorption of light. Now, light outside the capture cone, we're all distracted by the fact that this is quite bright at the edges. But if I hold up to the screen, why is the screen red? That's light that's escaping through the surface, right? That is actually between 30 and 50% of the light. So it's a big loss, and nobody had tried to go after that before. So I decided, okay, let's try to keep that light in and try to get that out of the sides. Before I go there, though, I'm going to have to do a little bit of discussion because not everybody's aware of liquid crystals. I think everybody's carrying it in their pocket, but not everybody knows how they work. So I'm going to talk a little bit about this fourth state of matter and how I can use it to try and improve the performance of a luminescent solar concentrator. So normally, we all know that materials have a crystalline state, and then if you heat it up enough, it will melt and form an isotropic state. Well, a liquid crystal is simply one that has an intermediate or a mesophase state. In this state, it is a liquid-like. The molecules can slide past each other, but the molecules are all facing more or less the same direction. So it's like an ordered liquid. Okay, so a liquid crystal looks more or less like one of these things. You've got a central core that's a stiff object, so like a stiff rod, and then you've got long floppy tails on the edge. This allows it to be liquid, allows it to move past each other. This part keeps it in line, some sort of order. So the anisotropic shape leads to both anisotropic optical and electrical properties that we'll exploit. So it leads to dielectric anisotropy. You have a different dielectric constant along the backbone and perpendicular, which also means you have a refractive index anisotropy. There's a larger refractive index for light traveling along polarized in this direction or this direction, which we're going to make use of. So it has 2 refractive indices. It's a birefringent material. And because of dielectric anisotropy, we can cause it to switch, is what happens in your cell phones. Electric fields, you can switch these and make a shutter. So I'm going to use both of these features in different ways with the LSC. The other thing to know is that these different phases are attained by temperature and in a very simple way, by just spreading the material from solution onto a substrate, they will self-assemble and form an order. So I can make all the molecules lie down, which is called planar. I can have them all stand up from the surface, that's homeotropic. I can have them standing up on one surface, and then at the top, they'll be planar, that's called a splay. And I can have a twisted state. So in this talk, I'm going to talk about the planar, homeotropic, and twisted states, and show how I can use these to affect the performance of a luminescent concentrator. Now, these alignments can be attained in many ways. You can use electric fields, you can use magnetic fields, shear forces, or you can use just a simple layer on a surface that you physically rub. And then this surface will direct the molecules how to stand. So it's something you can do completely hands-off, they will self-assemble. Another thing that you can do by making them reactive, by adding an N group to the floppy chains, for example, an acrylate group, you can then photopolymerize them and take this structure that you create and then fix it into a permanent film. Okay, now I've talked about the liquid crystals. Now I'm going to talk a little bit about dichroic dyes. I think many of you already know about dichroic dyes, but I'm going to say it anyway. So dichroic dye is essentially an extended molecule such as this coumarin here, where if you have light polarized parallel to the dipole axis of the molecule, it absorbs very strongly, and perpendicular, it absorbs very weakly. So we have a UV-Vis spectrum, parallel and perpendicular. I'm going to talk in this talk about an order parameter. An order parameter is a measure of this ratio, and it's done by this formula here. The amount of light absorbed parallel minus amount perpendicular divided by parallel plus twice perpendicular. If you do this, you get numbers between 0 and 1. 0 means it's completely random, totally isotropic. 1 means perfect order. Okay, so as a reference, liquid crystals that I work with usually have an S value of about 0.6. So if I get a dye that is getting close to 0.6 order parameter, that means it's aligning about as well as the liquid crystal. Okay, so last thing about the dichroic dyes, they don't only absorb anisotropically, they emit anisotropically. That means if you have a dipole axis along here for your dye, the emission profile is more or less perpendicular to the directionality of the dipole moment. Okay, so I want to put all this together and try to then say, okay, I'd like to improve the performance of a luminescent concentrator. How can I do it? Well, what if we take the liquid crystal and put a dye in it? So liquid crystal is a rigid rod with a floppy tail. The dye molecule is often a rigid rod. So here's an example dye, example liquid crystal. They're both kind of rigid rod segments. The liquid crystal can be used to line up the dye molecule. So the liquid crystal will dictate the alignment of the dye. So if I then add an alignment layer, I could then align the dye molecules to either stand up or lie down on a surface, following that of the liquid crystal. Okay, now let's make a luminescent concentrator where we lie the dye molecules down on the surface. This one's random, so each edge is emitting the same. That means I need 4 solar cells around the edge. What if I could reduce both the number of solar cells I need and make it easier to tie all these things together if I could put the solar cells just on 2 sides? How could I do that? If all the dye molecules are lying down in one direction on the surface, the emission is more or less directed towards 2 edges and not all 4. So that's what we did. We took 3 different dyes. In this case, this one, which didn't order at all. Remember, this is the order parameter, gives it a degree of order. So I put that in a liquid crystal, but it didn't align in that liquid crystal. I have this orange dye, which is intermediate, and then this coumarin dye, which aligned almost as good as the liquid crystal. Then we look at the output ratio. So how much light came out parallel to the dipoles of the dyes, and how much came out perpendicular. And we can see 50 to 60% more light came off of one edge parallel than perpendicular. And if you extrapolate this out to perfect order, then we're on the order of double. So we get twice as much light from two edges than the other two. So we've halved the number of solar cells that we need, and we've also dramatically simplified how to wire this thing together and put them back to back, for example. Well, you said you might say, you showed me planar. What about if I stand them up? So we did that as well, stand them vertically. So in this case, this one is looking at surface loss. So this is how much light we lose to the surface as a function of the perceived absorbance. I say why perceived in a moment. So if I have an isotropic sample, which are the light gray circles, you see I lose between 20 and 50%, depending on how much dye is in there, of the light from the surface. Huge losses. If I have it planar, it can even be a little bit higher. If I have homeotropic, so this system actually has as much dye in it as this one. It doesn't look like much because nothing's getting absorbed. The light, the dye is perpendicular to the light source, so it doesn't absorb anything, but what it does absorb, nothing leaves the surface. So we've eliminated surface loss. Unfortunately, we've also eliminated absorbance. So somewhere between the vertical and the planar is the way to go. And you're hoping the next slide would show the perfect one. Well, it's not so easy getting a tilt angle on these things, so that one I can't show you yet. But if anybody has a good idea on how to get a nice tilt alignment, then come talk to me about it. We've tried some more exotic alignments. So instead of just everything lying in the same direction, we've also done, for example, we called this the opera seating. So we have all the dye molecules lying along these lines. This is the rubbing direction of the liquid crystal. So you can see, well, maybe not from the back, but if you look through cross-polarizer, you can see indeed we have the correct alignment. Everything's in the semicircle. And what this is, it's a measure of an intensity of light that you would measure along an edge. And if we predict, if you put all the dye molecules in and predicted where the most light would be concentrated, it's exactly what we see in our sample as we rotate 4 samples. So we can concentrate the light, not just over an entire edge, but at a smaller fraction of that edge, which means we could use a more efficient cell that may be tuned to that wavelength and really increase the efficiency. You can imagine other ones. The ultimate is to have a hole in the middle and all the dye molecules facing the middle. We've done that before, but I have no flexible solar cells to put in the middle to measure it. So I don't actually know what our output was, but it should be the best one, but okay. Now, one more chemistry slide. You probably all remember this as well, but just in case you don't, I'm going to talk about chirality. Chirality is when you have a molecule that cannot be superimposed on its mirror image. It's called chiral. So if we take a liquid crystal, a nematic liquid crystal, so the liquid crystal phase, and we add a chiral dopant, it tries to accommodate this chiral molecule, but you've got these little bits sticking up. So what it does, it causes the layers of liquid crystal to be twisted with respect to the previous layer, right? So there's a slight rotation to be able to accommodate these molecules. So you've got a continual twist through your sample. So this they call the chiral nematic or cholesteric phase. It's called cholesteric because it was first discovered in, as you guessed, cholesterol in the body. I don't know if any of you ever work with meat, but if you cut the meat, you kind of see this glossy, iridescent sort of film over the red meat in the fat area. Well, that's cholesterol that's in this twisted alignment. So why does it have this reflection? Well, remember that these are dichroic birefringent molecules. So a high refractive index and a low refractive index. So as you go twisting through the depth, you go from high to a minimum, to a high, to a minimum, to a high. That may remind you of a Bragg reflector. A Bragg reflector, like you see on mylar balloons or sometimes on tennis shoes, this nice reflective surface. That is variations of high, low refractive index material. Each interface of high and low refractive index, you get a little bit of reflection. If you continue doing that through a surface, then you get more and more reflection. So A right-handed cholesteric helix, which you make by simply adding a chiral molecule to the same liquid crystal, it self-assembles over a surface. So very easy to make. In fact, I've got a couple demos here. You can take it out of the baggie. I don't know if you've seen a cholesteric before. You can take it out of the baggie. There's one on a glass plate, and there's another one that I put directly on a luminescent solar concentrator. So I'm giving away the idea of the cholesteric. But the more chiral dopant you add, the tighter the pitch, which means the shorter the wavelength that we can reflect. So just by changing the amount of chiral dopant, we can get any reflection wavelength that we want. So if I need blue, I add 5%. If I want red, it might be 3%. That's it. So if you try to do this with inorganics, you have to very fine calculation of how thick, for example, your titanium dioxide, how thick your silicon oxide, individually deposit layers 20 times. That's very tedious. This is done out of solution. So it's got a great advantage. The disadvantage is that light of the opposite handedness, so sunlight comes in two forms, right and left circular polarized. The right circular polarized in a right-handed helix gets reflected. The left circular polarized passes through. So to get full reflection, we have to stack a left and a right. So that's the biggest challenge, let's say, on the cholesteric. So all these equations, you can calculate exactly the wavelength you want. The other challenge, as you might know from Bragg reflectors, and if you pass this sample around, look at it by tilting, it changes the wavelength reflected. All right, so if you look at it straight down, it might be red. At an angle, it is reflecting green. Okay, I think you can, well, here's an example here. This is on the edge of a glass jar. So you can see in the middle red, at steeper angles, you can see the same reflectors green. So you can probably see where I'm going with this. I got this red plate that absorbs green light and emits red. What if I can let green light in, but red light reflects? It can't leave the surface. So everything would have to stay inside. That's the idea. The problem is with the angular dependence, sunlight, unfortunately, doesn't stay static in the sky. The damn thing moves. So noontime, perfect. I'm reflecting my green light's going through, red's reflecting, perfect. But about 3 o'clock in the afternoon, this is reflecting green, and my light that I want to go in gets reflected away. So there's some tricks that have to be worked out to make it function perfectly. But we've done this work, basically, oops, I get too excited. Right, so light comes in, you can't let it get out. What we did, we changed the effective reflection band for this dye molecule. So this is red 305, a very standard dye used in the field, absorbs about 550, emits about 630. And you see the best performance I got, they had a reflection band that was actually, let's see, on the order of 810 nanometers. So way out here. Why is that? Well, a lot of light that actually gets emitted from the surface goes from high to low refractive index and goes away from the normal. And so that means a steep angle, which means we have to have a reflection band out here. But if you choose it correctly, at this point, I increased edge emissions about 5 to 15%. And considering it's losing 20 to 50%, I'm collecting most of it back at the edges. So it works. Okay, now the next thing was, these are static. Can we make a luminescent concentrator that's dynamic? Why would you want to make it dynamic? We can imagine something that inspired us was the office room. So bright sunny day in this office, but somebody near the window finds it too bright. They've closed the shutters, they've got the lights on. What a waste of sunlight, right? So what can we do here to try to, let's say, adapt our windows to the condition of the sun? I know you guys do it in several different ways here. So I'll go over the ways that we've approached it. We basically make an LCD screen for the window. So we take 2 glass plates and put a liquid crystal in between, and in the liquid crystal, we put a dye molecule. In this case, we put a fluorescent dye molecule. Incident light gets absorbed by the dye molecules, creates the emission that gets trapped in the glass planes of the window, travels to the edge, which we can generate a current in a photovoltaic cell. So this is during the working hours, right? Brightest sunlight, we can generate energy and we don't use any energy. Then let's say in a couple hours in the evening, before you go home, you'd like to open it up again. You use that energy, to give a potential across the window, you switch the dye molecules, then light can enter. So we have a couple examples. This is an example of one of the switching windows. So of course, your first thing you say is, we don't like red. Well, that's okay. I mean, you can mix dyes. This is just a sample, but you can see between 0 and 10 volts, we get pretty good switching on the window. This actually was one of the spin-offs that we did. Originally, it was called Pure Plus. I was an idiot and I just acted as an advisor, but I didn't take any shares. Well, it got sold to Merck. It's now EIRES. They got sold for like 15 million. And my wife said, yep, you're an idiot. You're right, but okay. But now they're getting really, really beautiful architectural type of glass that they can switch between a dark and a light state automatically. They are not using the photovoltaic system at this point. They are actually gaining advantage just by the fact that it keeps the room cool as well. So if and when they go back to adding the photovoltaic part, then they might be able to switch the window autonomously. Okay, so that's just a 2-state window. We'd like to increase the number of states. Of course, more complicated is always better. So we're going to try to add a privacy state to the window. To do this, we can use the same liquid crystal type of cell, but now we're going to do, instead of the regular cholesteric twist, we're going to do something even cooler called a super twist. All that means is you make an extremely tight twist on that system. So instead of a slow rotation, it's very steep rotation. What that does is light normally, if it's a slight twist, the light will follow the rotation. But when it's a super twist, it can no longer follow the rotation and you can get types of scattering states. So what do we want to do with that? So here's an example of a window. We first have a kind of a dark state. We can make an intermediate scattering state at middle voltages. And then at higher voltages, we can get it to go fully homeotropic. We get transparent. So we've got a dye in there. In this state, you're absorbing light, emitting it to the edge, generating some electricity. This one, you're having a privacy state. And then the last one, you can make totally transparent. So why did we put this little picture of a plant at the back? Well, first I'll do the intermediate. This is just to prove, hey, it works. This is just if you use a dye molecule, but then if you use the super twist, then you can also get this scattering effect, which can gain you a little bit of extra light as well. Our thought is, how about a greenhouse? Greenhouses have, the plants have different lighting needs at different times of the day. When you have high intensity light coming in, you can probably take some of that away and just generate some electricity to do something else with it. Maybe run a fan, maybe store it for some of the lighting at night. Sometimes you've got the light, but it's all direct light and you like to scatter it. You want to scatter it because you'd like the light to go deeper into the leaf canopy. So it's known that if you can scatter light, you can go 6 or 7 rows of leaves deep rather than just the top 3 or 4 getting light. So you can get more per plant. Or on a cloudy day, you just switch it and then all the light will go through and then you make the maximum use of the sun. So that's an idea. We can have a greenhouse, generate electricity. You can also change the color of the light, which can also assist in plant growth. Plants really love near infrared light, and they like, they have to have some UV, but they really like near infrared. Green, hell, they reflect most of it, right? That's why it's green. So why not use the green for something else? Anyway, that's the concept. I'm not a plant biologist, so it sounds good to me. Okay, that was done electrically. We'd also like to be able to do this type of thing thermally. So this is a sample that we have 2 states in a liquid crystal that's in the nematic state. And when we heat it up, it goes isotropic. And completely by chance, we had this dye from a collaborator that we wanted to put in a window. We put it, well, he made it for us and he asked us to put it in the window to see if it's going to be aligning much better with these tails. Oh, this is going to be great. We put it in the window. It really sucked. We didn't have the heart to tell him. We said, oh yeah, that was okay. But we were going to toss these things around because they didn't dissolve. It just sat there. So then I told my student, what the hell, heat the thing up. Why? I don't know, just heat it up, see what happens. Well, what happened was marvelous. It separated, spread through the whole thing, and then suddenly we got Foster resonance energy transfer. It got near to the yellow dye. We could then absorb all the yellow light and emit red. So we got something that went from a bright yellow color to a bright red color And what amazed me, it goes back and it goes back and it goes back. We've done it 30 times and they look the same. So that's cool. I have a video. What you'll see, the first thing you see, so the green and red are in here, but the red is in a crystalline state. You can see here, we've gone to the isotropic, the liquid crystal is now melting. We're in the isotropic state, and as you wait for a bit, you can start to see it slowly change color. And if you're patient enough, eventually the end is pretty much all red. And if you were trapping it, let's say halfway through, you can get any color state in between that green and that red by stopping it and just sitting at that temperature. If you sit in the intermediate temperature, you've got kind of this orange. If you do it at the later temperature, then you get this red. So that's all driven by temperature. We think, oh, this would be fantastic potentially for a greenhouse. I have found from one company that they have 8 different colored light they use for orchids, but they generally lift all the orchids individually and move them to the next light source during this plant growth. Well, what if we could control it this way? The problem is right now, these are changing at 60 or 70 degrees, so probably not so good for orchids. But anyway, so that's something we can do to try to improve the performance if someone finds it useful. So we put them both together. So this is a more complicated, you can either switch it electrically or you can do it thermally. So this is one of my philosophies that I think we all like to make automatically responsive windows. The idea is, okay, people are dumb, right? We just want to make it easy for them and just have a window to change. However, I've done a lot of work or discussions with people that do human psycho intellectual discussion and how they approach science. What people think they want is something they can control. So the idea behind this is for the first 2 weeks they have this, they can go nuts and switch this every time, and oh yeah, we got this, we can control it ourselves. Then when they forget about their new toy or lose their controller, then it will still switch when the temperature is at the right spot, right? That's the idea. So this is the type of thing that I try to build into our systems. Let people feel they have some sort of control, but then, make sure it's still going to work anyway, right? Okay, so we have some other color effects. This was also completely random finding. Actually, it's because I screwed up. I didn't take very good notes in my notebook. I have a red dye that I assumed every dye under mankind's and womankind's production would align with the major axis along the liquid crystals. It always happened, so I figured it always would. There was one dye that didn't. It went the other way, but I reported it like it did because I didn't pay attention to my notes. I had to write a retraction, well, at least a correction in my next paper. Luckily, I hid it in the notes at the end, the references. I hid it in the references. So I didn't come right out and say it. I kind of said, oh yeah, by the way, last time I got this one wrong. It's the other way around. But it's a good way to do it, right? Because you're honest about it, but nobody reads the references. Unless you're looking for your own name, of course, then you want to see if you got referenced. But this one, if you change the polarizer of this sample, you have 2 very different colors because the 2 dye molecules are aligned in different directions. There's the same effect if you switch it. So if I switch it between the 2 states, I can switch between these 2 colors, visible colors. Is it useful? Don't know, but at least it's something that you can do. And if you have a purpose for it, hey, come talk to me. Okay, another application. They're not only for electricity generation. So in this case, what we wanted to do, we were inspired by the leaf. So the leaf is a very simple device. It basically collects photons and it transfers the energy over a distance to a reaction center. So we said, okay, can we do this to do photochemistry? Can we make our system like a leaf where we collect, let's say, light at a distance, we transport it to a region that we want to do a photochemical reaction and then drive the reaction there. So we have a system that has a catalyst that works very, very well. This is the blue spectra. So this is the wavelength you need to catalyze the reaction. The solar spectrum in gray doesn't have enough energy here to effectively catalyze that reaction. However, if I use the red dye and collect all this light and transport it into this green spectra, then I've got enough energy to drive that reaction. And yes, indeed, we find out that we can increase the conversion of this chemical reaction driven just by sunlight. We made a system, we put it outdoors, and then we also added a little detector to the outside of the luminescent concentrator. So we also use the edge light. The edge light tells you how intense is the sun. If it's really intense, then drive your pumps really quickly because we can get conversion very quickly. We've got plenty of light. If the sun goes down or there's not much energy there, slow those pumps down, let it sit there longer, and then we can get full reaction. So we maintained the same level of production despite the sun condition. So at all times, we had the same conversion efficiency, which is something that people like. If you don't put in the dye at all, then the system basically follows the sun with a very low conversion, but put the dye in and adjust the pumps, and then you can get a very continuous conversion for the full time. So we're working on a larger prototype. This is then a larger 50 by 50 centimeter to 1 by 1 meter system with a bunch of reaction channels we flow our liquid through. We have a solar cell underneath. So everything that isn't absorbed by this panel will go to the solar panel, so it doesn't take any extra space. That's enough to drive our 3D printed pumps, which then send the material through. And this is an example of the type of prototype. And the idea for this one is we did an experiment on using a natural substance that comes from leaves that you find in the Amazon. And you can do a photo process that makes a rudimentary malarial drug. So is it a perfect drug? Is it as good as the best? No, but it is an anti-malarial at a specific level. So the idea would be you could take this device out to the jungle. The only thing you need to bring with you are the correct solvents. You can take the local leaves, toss them in the bin. Sunlight will run the reaction for you. Sunlight will run the pumps. And all you have to do is just wait for your drug to drip out the other side. So we're currently talking with NASA. They're interested in trying to take this to Mars, which would be really cool, but I doubt it's actually going to work. But still, it'd be kind of cool to send up one of your things on the Mars to see if you can generate some sort of chemical there just using the local materials and sunlight. So the other nice thing about this and other LSCs is that you can reuse them. So in this case, they used a rather complicated, all this tubing is in there to help the mixing. So I don't know anything about mixing, but they need to have all these channels to get things to mix better. But these are really expensive. But what we can do is we can make a red one and we can simply peel off that top layer. It's just a dye in an acrylate or a liquid crystal and put on a yellow. Or put on a blue. So we did that, and each time we find out, well, except the blue, we don't have that much blue light in the sun. But the others, we can accelerate the reaction using the same reactor, and all we have to do is just change that top coating. So the expensive part, you reuse as much as you want, and this part is just going to be a few euro cents to replace. Okay, I'm going to close up, but these are some other related projects. We're working on the beautification, so trying to make mosaic luminescent concentrators, so little blocks, but then you can make all sorts of funky images with these little blocks and also generate some power. We have forced resonance energy transfer systems where we get a dye to go into channels and have other dyes that are nearby, and so you can get, let's say, energy lossless transfer from shorter wavelength to longer wavelength. We've direct ink written these, and that should have been a video, and unfortunately it's not working. But in that one, we've printed the high in 2 different directions, so you get nifty optical effects, although it doesn't look really good because the first try at 3D printing didn't go so well, but okay, that's why it's still research. We looked at, let me try again. Okay, I'll just do it this way. Back one slide. Different keyboards. Yeah. Static windows. So we just did a study to see what people thought if you covered just the top of a window with a luminescent concentrator, could you still make it work? Would people still accept that? And actually, they found that if you cover the top 25%, the way that it made the roof look, and since people weren't looking up anyway, they rather liked the appearance of the room. So it might be possible to generate some power even with something that's really brightly colored, as long as you don't try to do something like cover a whole room. And last, we had a light responsive color change. So this one I liked. We went from totally transparent to a yellow fluorescent color. with a light change. So depending on the lighting conditions outdoors, we can also affect the appearance of our system. Then, in conclusion, I want luminescent concentrators to complement photovoltaics, not replace them. Where you normally use photovoltaics, leave them there, but everywhere else you can use an LSC, and that's a lot of area. Low power, large area, attractive appearance, you can demystify solar energy for the general public. I mean, there's a place in America, in South Carolina, that the town petitioned to have the solar panels taken away from this field because it stole their sun, and they're afraid of kids getting electrocuted when they touch them, right? So they're scary looking, they're high tech, ooh, but nobody's afraid of this, right? Nobody's afraid of this except for the fact, yeah, you have to recycle it and all that, you're killing fish, et cetera, et cetera. But in general, you don't feel you're going to kill yourself with it. They're not only for power generation, you can use for lighting control, fine chemical production, and other potential applications. But we need a larger scale coordinated research. And that's something very difficult at the European level because of the perception that these are just bad solar cells. And so we always lose out to a solar cell project. However, we need to have an approach that can show the additional, what we can add to the solar energy environment. I just want to talk a little bit about our group. What we try to do is also things that we can't find that people want to pick up, we try to spin off ourselves. So these are some of the groups that we spun out over the years. Some of them survived, some of them didn't. But as I was talking to Claudio, don't give up. You know, they still can, sometimes they still work. So this one made some guys millions, and this one really was a pain in the ass. So it depends. Last, I just got a slide. Of course, it's a little offset, but these are a lot. There's been a lot of people that have worked on this, bachelor's, PhDs, master students, people in other universities. I'm sure I missed some, but yeah, I want to thank them all for all these great ideas. I'm always open for new ideas. So if anybody is interested in this and would like to chat about it, love to hear from you. And again, thank you much for the invitation. And I hope I didn't go too over time. So thank you very much.
Thank you, Michael, for this nice presentation. Now it's time for questions.
Sure.
Yeah. So I'm wondering about making these panels, for example, very, very long.
Mm-hmm.
At some point, you're going to hit the trade-off between how long you're going to make it, sort of long range absorption. So what is this trade-off, and is there an ideal size and ideal width?
Yes, yep. And the answer is you lose a lot. So for these panels, actually, we didn't put any on the far edges. That wasn't worth it. We put them just on the top and bottom. And even that, 10 to 20 centimeters. So light in the middle never got out. One of the problems that we had was this particular die and this particular panel wasn't made that great, and it was way too scattering. So that was a lot of loss. We actually were about a factor of 9 less than we wanted. But I think that solutions are on the way. For example, quantum dots that have that potentially have a much larger Stokes shift, so distance between absorption and emission edges. So what I like to think is I'm getting ready for when they have a better die. As we have now, yeah, it's on the range of 10 to 20 centimeters. So if you make something larger than that, then you're going to be losing some that won't be able to get out. But at the same time, it depends on the function. So the noise barrier, no matter if the light comes out or not, it blocks noise. And that's the main job. So we tried to sell it as the main thing is an attractive noise barrier. Secondly, you get some power out. And if it had performed as we felt it should, then we had a payback time on extra components of 8 years. With a lifetime of 30 years, that means you have, 20 some years of some payback on your normal panel. So it won't pay for the whole thing, but you'll pay for the extra component, and you can use that power, for example, to run emergency phones. So you don't have to run cables. In the Netherlands, since they have to be like 1.5 meters deep, it's like 1,000 euros a meter to lay those things. So if this one is local, yeah, you don't have to go all the way from town, out into the middle of somewhere in the desert to run these cables. You can just do it local. So that's kind of the idea. Low power things, but with high impact. But yeah, it is a payoff. We can also, and then there's also doping. How red do you want it? If it's less red, we can actually get the light a lot farther. So it's if you like them being more pink than red, then hey, that might work. So
what about phosphorescence?
Phosphorescence is usually the quantum efficiency is so low. The other thing, of course, that we would love to have is an up conversion. But yeah, generally then you need to have concentrations like 100 times or 1,000 times. We're not there yet. But all of these things we would like to do. I mean, one thing that helps with the signage, because we just print small areas, almost all that we collect gets out. So there's almost no reabsorption in those. But then, of course, we only collect so much because only so much of the surface is covered. So it really depends on your application and how much you need. They don't need much there because LEDs don't need that much power to run.
How do you measure the edge emission?
Yeah, so we have an integrating sphere. So in that one, it's ours has an aperture of about 5 centimeter hole in the side. We make a little slit in that in a cover, and then we can place our sample. So just the edge will illuminate into the sphere, and then we can shine light from, in our case, a solar simulator on top. So then we can measure all the 4 edges, which is important for the aligned dye system because those are different. So it gives a lot of flexibility, but we're limited because of the size of our sphere to about 5 centimeter samples. Or they can be 5 centimeters in width, but very long by just extending it back. So that's how we've done some of the distance measurements. But yeah, it's a relatively cheap but very efficient way to do it. And we have a couple papers on how to give it a go if you want to try it at home. So,
do you need a specific integrated sphere?
No, I mean basically if you get a detector, I mean the normal detectors you can buy that are reasonable, 1,200 euros or something like that, will go from 400 to 800 nanometers, which is good for most. We've got the little bit, we can go a little bit farther towards 1,000. That'll cost you a couple thousand euros. The sphere itself is a few thousand. But yeah, you have a pretty good measurement system because then you can, well, in various ways, you can calculate your efficiency, you can do your photon efficiency, you can measure the quantum yields at the same time of your system. So you can get a pretty good indication of the light effects of your system. I tend to do light to light rather than reporting an efficiency with a solar cell attached, because, and that's one of the problems of the field, is how do we report a luminescent solar concentrator performance? You can give an efficiency. So I could give this, if I told you, okay, this efficiency, well, I'll make up a number, this is 3.2%. If I had a yellow one, that could be 2.8%. Which one's better? We say, oh, obviously the red one. The yellow one might be 99% efficient in getting the photons out. This one might be losing 60% of the photons, but it's absorbing more. So what's the fair way to compare them? Just by output efficiency? If you do that, I have no idea from the literature when people do that, is their material better than mine? Are they losing from their plastic? Are they losing from the dye? Is there reabsorption going on? That's all hidden, because you've just got this one efficiency number, which is photons in, electrons out. But what I'm interested in is photons absorbed and electrons out, or photons absorbed, photons out. So that's what I use the integrating sphere for. But yeah, so that's a big, in the research community, that's a big controversy, because everything in the literature until 2018 was some efficiency. And those were lies like you wouldn't believe, because people would put on a gallium arsenide cell specific to that wavelength, and they'd make something about 2 square centimeters and claim a very high efficiency. That's absolutely untenable. No one can make, a meter long type 3.5 cell for any sort of cost, but they got a record efficiency, right? So they get cited a lot. My sample might be 2.3% efficiency, but using normal dyes, cheap cell, whatever. So it looks terrible, but it's a lot more economical than the other one. So that discussion is very difficult. So there's a couple papers now that give ways that you should report them. And I think we're moving in the right direction. So then we can start really talking about how to implement these in the built environment in a reasonable way.
Thank you for the talk. It was super interesting.
Oh, thank you.
I was wondering, you mentioned the scattering
Mm-hmm.
as an effect that can improve the efficiency. Do you think it can be exploited also in parallel with photoluminescence?
Yes. So oftentimes, what you do if your main goal is just to get the highest output you can, then put this on top of a white painted wall. So all the light the dye doesn't absorb gets scattered, and some of that just happens to go to the cell. So it's a just happens effect, and it's usually only 5 to 10, say 5 centimeters effect. But if you paint the back of this light guide around the edge 5%, I can at least double the output. Of course, it changes the appearance. So it's how much you want to give up for appearance. Oh, if you do that, make sure there's an air gap. So if you paint this directly, then you lose almost everything, because everything that is light guided hits that white layer and gets scattered. If you have a small air gap, then you get both the scattered light and you get the dye light. So if you want maximum output, then come up with a nifty way to put a white edge around it. We did that on the noise barrier. We put a little bit of a white edge so we can get a little bit of extra power out.
Thank you for the talk, very interesting. I would like to know if have you ever tried with another cholesteric structures like cellulose nanocrystals, for instance?
So the cellulose nanocrystals are quite difficult to modify and to play with. So we have not. We have taken, let's say, regular reactive mesogen chips, so flakes that we put into a binder. The only thing is then it's a beautiful effect. It's a very shimmery effect, but it's very random. So it's much more scattering. So the nanocrystals are similar. We have another project. We're trying to manipulate them, but they're tough. The nice thing, of course, is they're organic and you can just get them, they're very green. So that would be a nice thing to go to. But at the moment, we haven't found a way to apply them here that preserves the integrity of the light guiding, for example. You get a big scattering mess.
Another question. What is the process that you coating these kind of surfaces, like spin coating?
Oh, yeah. So you can do many different ways. So the smallest one's a spin coat. That's easiest, but you can also bar coat. We spray coated. So we went out and bought a little model car spray kit and just sprayed that way. Works really well. We do inkjet printing. And now we're starting the 3D printing. So there's a whole variety of ways. They have differing, so example, bar coating, that takes a lot of skill to get a very uniform, consistent layer, but they can also be quite nice over large areas. Spray coating is very nice, but it's, since we do it by hand, that can be really annoying to try to get a uniform coating. You have to have, the right pressure, the right sweep speed. And so a couple students wasted their bachelor end project on doing that. They looked okay. And then the inkjet printing is how you get the really, really nice images. And that one we like a lot. So that's the spin-off that's working on that.
For the spin coating, I guess it's in the smaller area. But do you have, because I saw your sample, radial alignment, right?
Yeah.
So it's something to do with because you have chiral response. So maybe it's influenced because you have the chiral distribution, maybe it's give you some advantage of the,
So we do sometimes put the dye within the liquid crystal. So, and there are other people that do this inside the chiral liquid crystal. If you do it right, if the reflection band matches the emission band, you get a kind of lasing in the system, right? Because the light can't get out. It keeps on bouncing eventually, so you get this lasing edge. We haven't tried to do that with a luminescent concentrator type of thing, but you can, people do that, putting dye directly in the chiral system. We have done it as well trying to get different effects of putting dyes in and polarizers in different sort of liquid crystals. So we do all sorts of funky optical things for like security features. Like if you rotate it this way, you see a duck, and if you rotate it that way, you see, a famous figure or something like that. But we haven't found a way to really use that type of system in an LSC. But yeah, like I say, this is a third of my life is LSCs. So you can come talk about other ways that we use the materials as well. We can do that sometime.
sir. So I'm more interested about the alignment of the dies,
Mhm.
liquid crystals.
Yep.
So I want to know that which type of liquid crystal you mainly use for your purpose.
So the switchable windows, the most standard one, there's something called E7. It's a mixture of 4-biphenyl. Yeah, so if you know E7, that's the usual one that we start with. If your dye doesn't dissolve in E7, it ain't going to dissolve in a liquid crystal. So that's a good start. After that, if you want to go to the reactive mesogens, there are a wide variety, namely from BASF or Merck. I can give a bunch of names, LC242, RM257, RM82. There's a bunch of standard ones that we use. Those are commercially available. And all you need to do is you need to tune a mix to get the right thermal effects that you want. You want the pneumatic phase in a certain range. Then you need a photo initiator in there. And then you need an alignment layer. So, and a solvent, and that's about all you need. If you want better alignment, you need a surfactant, and there's several of those available, but it's a very simple 2 or 3 part solution. And then on glass, polymer, I've done it on rubber hosing before. I've done it on all sorts of different substrates. Just rub that substrate, and then you get automatic alignment. So it's really simple and straightforward. So if you want to play with it, yeah. First thing to do is get a little E7 and a cell, and then put whatever dye you want to and see if you get it to dissolve. And like I say, if it doesn't dissolve in that, it's a good chance you're going to need a different dye. So.
Thanks for the question. So my question is about the shape, because it's basically square or rectangle.
Mm-hmm.
So is it possible to have like a hexagon or triangle?
Absolutely, you can do any shape that you like. Now, will it affect efficiency? Yeah, it can affect it a bit, but then it's a question of, let's say, appearance versus output. I found many architects really came to me and said, I really don't give a crap what the output is, but I want it to look good, as long as it gives me something. Either as a PR state, you know, that we have a energy generating facade. It does generate energy. It might be 3%, but it's generating, right? So the other nice thing about them is you can buy a square one and just cut the shape that you want. So you don't have to mold it that way. You can just cut it. And that's a great advantage over a solar cell. Because whenever you cut a solar cell, you can cut solar cells in other shapes, but it dramatically can affect their performance with all sorts of cracking and edge effects and all these type of things. But this, if you wanted to stick it over a doorknob, just cut a hole in the middle and stick it over your doorknob, right? It'll still, the active area still works as normal. So in that way, you have a tremendous advantage. You can also give it surface structure. So we have some that are shaped like a tile, a roof tile. You have to play around with the shape to make it gradual so you don't lose the light guiding, right? If you make it too sharp a peak or something, you'll get some light that emits from the corner. But if you're careful about it, you can have many different shapes, many different surface features. So those are, and in that way, for a designer, this is really ideal because you can make any sort of image and then print an image on, you know, an odd shape, and you can make any sort of device that you want, that you can imagine, and it'll generate some power. Is it going to be the solar panel? No, but it will generate more power than the painting over there, for example. That's not doing anything. So you can gain some advantage. So that's kind of how we try to sell it, you know, and you can make an entire wall of it. So the whole wall might give you 1,000 watts or, yeah, 1,000 joules per whatever. And it's not as good, you know, you'd have 4 solar panels would do better, but then you have to find a way to display 4 solar panels that people like to look at. So
when you work with liquid crystal cells,
Mm-hmm.
how difficult it is to work on curved cells?
Oh, with a cell, yeah, that's more challenging. So we haven't done it so much. There are some flexible polymer substrates that we have acquired, but we've not yet tried to fill. But they have, generally you can directly rub the polymer and you can get your alignment layer. So that's an advantage of the polymer that you do. In a glass, you have to usually add an extra alignment layer to rub. but with the polymer, you can just rub the polymer directly. So that would be very straightforward. But yeah, it's basically, you'd have to add some spacers everywhere to keep the spacing. And we just haven't gone in that direction yet. But there's no reason you can't. I mean, they can make flexible TV screens. And our windows are essentially a TV screen, but we're just not experts on doing that shaping.
With color surface, there are more chances for losses.
If it's too sharp, sure, yeah. But at the same time, if you have a curved surface that's quite, let's say, a semicircle, light that leaves this surface can encounter that surface and actually get reabsorbed. So you can actually recover some of your surface losses. So it's not an automatic loss when it leaves anymore. So I know we had one student that did a little project on that. So does better than a flat in that way. But yeah, if you make it too tight, then you have problems on the light guiding.
Was wondering, what about the parameters such as stability, photodegradation, and
Yeah.
shelf life of these prototypes?
Yep. So excellent question, of course. That's one we often get. So the polymers, many of these are now to the state that they can last for a couple decades. You know, they're used in architectural integration. The dye materials, the red dye, that has a lifetime of probably 20 or 30 years in the sun. So that's really stable. The yellow dye is kind of crummy. That will probably go a year or two. Blue dyes, those suck. So that's what we're looking for. We're waiting for good quantum dots, because at least the promise is, being an inorganic, they're going to have a much longer lifetime. But the promises that we've heard now for 10 years, they're going to be long lifetime, they're going to have large Stokes shifts, and they're going to be cheap to make. I find them short lifetime and crummy Stokes shifts, and they last about a day. So it's still in progress, but I think if they get those sorted out, that's the biggest lossy part is the dye. But the red dye is extremely good. So that one you could start making now and could guarantee for at least a 20-year lifespan, as long as the plastic. The other components of liquid crystals, that one is more unknown, since there are examples of LCD screens that are deployed outdoors, sports stadiums that use LCD screens. So they have a certain lifetime, but I actually have not looked into so much what the lifetime of those are, what they guarantee. I would say in my experience, our reactive ones are not going to be able to last that long. However, something like the signage concept, one idea is you make the light guide transparent plastic, and you print on a foil that you stick to the surface, and then if you have a signage, you know, when you have the new special goes from the fish to the eggs, you know, as being on sale, you just peel off the fish one, you stick on the egg one. That'll cost a couple cents, you know, to print that. The expensive part, the light guide and the solar cells will stay the same. So that's one way we can mitigate the effect of the dye degrading. Now, if you have an entire building, that might be a problem. If you have the side of a bus, then if you had a lifetime of a year, that might be more than enough, because most buses, for example, in Eindhoven, change their advertising or change their exterior periodically. So that might be let's say, an application form that is not accessible to solar cells, but would be accessible to, let's say, a luminescent concentrator. And we overcome the biggest, well, besides the efficiency, we overcome the losses from degradation.
Is there any other measurement than lifetime to demonstrate that you got fret?
Oh, yeah, that's so I must admit I'm not a fret expert. So we did this with a guy in physics, and I was a little bit like you. It's kind of, how do we know we have fret? Well, see this, that's fret. All right. I know one of so the lifetime can be deceiving if you have too much dye in there, because you also have, besides just a immediate transfer, there can also be a reabsorption. So you have to be careful on interpreting it directly from the lifetime even. So what we usually call it is an indication of rather than proof of. And I think probably I have to go to more of an expert to give you a real proof. So for ours, it was, as we say, consistent with at least some degree of Forster transfer. because it was faster, and we saw one light and not the other, and we didn't see emission from dye 1. And so that usually indicates, that it's most likely going to have at least a component from the fret. How's that for a dance around answer for saying I don't really know? But it's we try not to be too specific and say this is. We say this is consistent with, and let somebody else prove us wrong. So.
I got a question. I agree with the fact that the best way to quantify this is about light in and light out, the combination with the photovoltaic cells. But I wonder, with that piece of plastic, what can we power? With the strongest amount of light that we have at midday, and what is an idea of what we can get?
So well, I can say for the signage, for example, so they made a sign that was, I think I showed you the Van Kampen sign early. It's well, it's 1.5 meters or 2 meters long, and from the sunlight during the day into a battery and then discharge the battery. So that's with the charging losses and discharge losses. They run it from, I think it's all, they can do all night for certain in the summer. And then on the order of, I think, to like 4 or 5 in the morning on a winter day, something like that. So that doesn't exactly tell you, but it's got a bunch of LEDs around the outside. So something like that is doable. I have powered, let's say milliwatt fans or things like this. I'm trying to give some other thought. I mean, the higher efficiency ones they would call 3%. We made our best was about 4.2%. So you can imagine then for a square meter, then you're going to get 42 watts. So that'll give you an idea what you can power. So.
And my other question is about the thickness. Is there any critical size above which we have to prepare this?
Well, thicker is always better, but then you have the payoff of cost of the polymer and the weight. So our standard is 5 millimeters. We find that the improvement you get going from 5 to, let's say, 6 or 7 is you've already gone, you're starting into the ramp over. Going beyond 1 centimeter or so doesn't help you so much, especially when you think about costs and weight. So generally we should go between, for the smaller samples, we're at 5 millimeters. For the noise barrier was 1.25 centimeters. We made it 1.25 just to make it nice and sturdy for holding, but it could have been 1. But like I said, if you made it 1 meter thick, then of course you'd have almost no reabsorption. But then you have to make a bigger cell, it weighs more, and it costs more. So it's a more of a cost benefit thing rather than performance.
And my last question is, on smart windows area,
Mm-hmm.
the neutral gray color is
Yep.
desired.
Yep.
So these are normally quite specific colors.
Mm-hmm.
So I guess if you want to merge different colors, you have the problem of reabsorption. So
but well, if you have, so that was the one I zipped by really quick. So back in here, if you get good fret, then you can go through 2 or 3 steps. If they're close enough together, then you can go in blue and come out red. And so you have no real losses there. So that's one way to get past it. If the dyes themselves, so the red dye, this dye has a measured quantum yield in solution between 99 and 100%. So this is, I mean, everything in comes out. The yellow dye is on the order of 95. So if you have them disperse enough that you have maximum 1 reabsorption or loss, okay, that's a 5%. That's not too bad. Of course, if you have 4 dye in series, it's 90, 90, 90, 90, then you're in the 60%, but still, I'd be happy if I got 60% of what I absorbed out. So I think it's on a reasonable size window, you could make a neutral color that would give you a reasonable output. of course, if you can make it, slightly more on the redder side, then it would perform a little bit better. But yeah, it all depends on what sort of appearance you want. But you can also play with it by adding a foil on the outside that's more neutral color to mask a little bit of the other color, and then still make it work as a neutral window. Yeah.
And what is the quantum yield drop passing from the solution to the solid?
Yeah, that's it can be high, especially, so these are all done. So in these plates, they're still quite high because the separation is still significant. So this type of plate, I can't say specifically this one, but doping similar to that has been measured, on the 95 to 100%. So that can still stay high. In the thin films that we print on, so these the signs, it drops quite a bit, because especially if you want a nice bright red color. If you don't care if it's pink, so like in the images they were kind of pink, the efficiency is okay. But if it's red, the dyes are getting close, and then it will drop into the 50 to 60% range. So it's significant. So that's a major thing that, well, that's one of the things the spin-off is working on, working hard on how to keep the dyes better soluble light, and a lot of that's going to be the host, and they're just trying to find the right host. But if you can, so they already are showing improvements. I think some of the first ones were like 19% efficient. I mean, everything just went dark because all the dyes would just crystallize. But they're getting much better now, keeping them separate. So I think that they'll probably get into at least the 80s or 90%.
Nice talk. I wanted to ask you, have you worked with glasses, revert, doped, or quantum doped glasses, and how is their efficiencies for as luminescent solar concern?
Yeah, so I have not personally, but there are people in the world that have done with it. In fact, one of the early pioneers in the field, Renata Reisfeld from Israel, she did a lot with like uranium-based glass and all sorts of things. And the biggest challenge that they have is they tend to have very narrow absorption bands. So the Stokes shift is fantastic. They get 200-300 nanometers, but they have absorption wavelengths be 10 nanometers wide. So there's just not much sunlight in that range. So in general, the quantum yield is not so bad. Of course, being an inorganic, sometimes they suffer a bit. So maybe it's 50 or 60%. They're not bad. And there's no reabsorption, but there's also no light coming out of the edge just because it doesn't absorb anything. So that's one of the biggest challenges with the straight crystals of the inorganics. Now, the quantum dots, as I was talking about before, there's a huge difference between commercial available and lab. In the lab, when they can clean everything, perfect everything, they can get quite good quantum yields. But as soon as you buy it from a company that claims 80% quantum yield, when we get them, it's under 10%. I mean, or as soon as you open the bottle, they start to react with air. It's a real, we find a real problem. So, because normally the people that make the quantum dots, the applications that they're for are just visual effects. And your eye can detect 7 photons that hit it. So almost no light do you need. So if anything comes off of there, then it looks quite bright and they're happy. But yeah, we actually want the high output for performance, and then the commercial dots just have not done it for us yet.
But I was talking about like quantum dot embedded glasses.
Oh yeah, yeah.
Inside the glass.
Yeah.
I asked this question because I worked on it.
But
I never got to this point to use them as a solar concentrator. Yeah. I just had the idea and.
So those I've not seen. So the last I saw where they really kind of embed, I'm trying to think if I've heard the quantum dots in glass. The problem is mainly the cost of making something like, I mean, whenever you put something in glass, it's quite expensive. So that kind of defeats the idea of something really cheap. I think the performance, especially now in the last 30 years, they're probably much, much better. So if you wanted to try to do, I mean, you could always send a sample if you've got one, we'll measure it for you. And we probably could write a nice paper, on a high efficiency doped glass. But I think as soon as you start thinking of actual commercialization, you're going to have a challenge on adaptability. I mean, you make this sheet is going to be really expensive to make, and it's not going to be so easy to modify between different samples to make different colors and all that type of thing, which with the organics tends to be pretty. One of the advantages we had, we can inkjet print it, so that's a very easy sort of application. But we don't get some of the performances that you might get with the dope glasses, which will probably last forever. But then it's I don't know anybody that's actually measured the output, but I think that the cost thing is probably why people don't do it so much. I shouldn't say it hasn't happened. I mean, now I'm talking, there's like a couple South Korean groups, I think, that put some into a glass. I don't know if they're perovskite, but that are still doing the inorganics in glass. So it's got a long history. It's been around since the 70s. People have done it. They've made measurements. They were reasonable, but it's not a major research line because I think of the specialty nature. Most people, like I can't make a glass in my my lab very easily because of the temperatures.
Okay, thank you for your answer. And about have you tried coating or changing the roughness of the surface to get rid of the emission that's going out and keep it inside the?
Well, if you roughen it, then of course you're going to destroy the light guiding, because what you want to do, if you have a perfectly smooth surface, then you can take advantage of the total internal reflection. So that's the difference. The refractive index inside and outside, there's a certain wavelength that can't leave the surface anymore. So if you scratch it, then it leaves. So that's actually a bit of a problem with these. If you scratch it too much, then you start getting some surface losses. But the advantage is if you scratch it here, only that part's affected. The rest of it works normally. Whereas if you crack or damage a solar cell, then usually the whole cell is out. And if you don't wire it right, the whole panel is out because that cell is bad. So we have some advantages in that way, but still you usually want to make it as smooth as you can.
And last question, what kind of, probably silicon solar cells, but is there anybody or you have tried any other solar cell to use in the corners of the?
Well, I would love, so I bought some type 3.5 cells at one time just to have high efficiency cells. What I think would be ideal is finding somebody that makes cells that are part like like a triple junction cell. But we don't need all three. We just need the one that's good at 630 to 650 nanometers. Then I think your efficiency will really go up. Yeah, we're converting everything just to a narrow band. So I think there we can have a great benefit. The main problem is the shape of our cells. Almost everybody that makes them has a standard that they produce cells, and they're either, well, in Eindhoven, we have Rene Janssen. He does organic and perovskite cells. We've never used one of his cells because he does 3 by 3 millimeter, and that's all. That's all they've got. Other places make 1 by 1 centimeter type 3.5 cells. That's it. They have no other way to do another size. So that's the biggest challenge. We want something that's 5 centimeters long and 5 millimeters wide. And just finding a partner willing to do that, we've not found. But what I think would be ideal is somebody that would like to print solar cells, print on our edge. I mean, how much better than that can you do? Organic cell, print directly on the edge, and then you've got a full system and make that print responsive to just the wavelengths that we need. We don't need blue. So one of the problems with organic solar cells was how to respond to blue, because they didn't respond very well there. I don't care about blue. I only care about red or green. Then you can make a really efficient organic cell in green that you could print. I just got to find somebody that wants to do it. So yeah, it's a different concept, on this type of shape.
Okay, so maybe there is a coffee there, so we can continue the question session, which is great. Continue there. So meanwhile, let's thank again Professor Debije.